Okay, so we're back here continuing to look at this idea of constrained diffusion. And I made another video before this where we introduced the idea of diffusion as this random movement. And we said that we're going to look at a scenario where we have an infinite sink here of concentrations of 0. And then we said that, and then we have some initial concentration here. It could be anything. We're going to assume it's a constant. And so what we said we think is going to happen, it's always important to think about what we expect. And then we're going to do a bunch of math, but we want the math to give us an equation that does this. Okay. Sometimes you may not be able to guess what it does, but it's always important once you come up with an equation to think about whether it's reasonable. So we said it should start here, and then because it's got these infinite sinks, that the concentration should then drop off to 0 and then be close to that initial value early on, and then over time it's going to bleed out to the sides. So we're like losing mass from our system here to the surroundings. And this problem is analogous to heat transfer problems, where if you have a really hot block here and you have two like infinite reservoirs where the heat is all absorbed, at the beginning it'll be hot and then it'll cool off, and this is exactly the same kind of problem and has the same exact math. It's just that instead of concentration there, you'd be looking at like temperature and thermal conductivity. So we went through that then, and we said we want an equation to do that, and so we could start with Fick's law, and his first law tells us that the pollutant moves from higher to lower concentration, and that's why there's a negative sign and a gradient. And so if we look at that in a differential element, we end up with Fick's second law here, which is a partial differential equation with time and space. And so then we can have the same equation for lots of different systems that have different initial and boundary conditions. And we're looking at the case here where we have these two reservoirs or infinite sinks and then an initial concentration. And so in this video now, we're going to start with all that and talk about how we can get into some of the math. Okay, I want to develop the first part of the mathematics here. So this is the second in a series of videos. All right, so let's move forward here. So we have dc by dt is equal to d squared c by dx squared. This is our model problem, and then we say c at x equals 0 is equal to 0, c at x equals L is equal to 0, and c at t is equal to 0 is, we'll say it's f of x for now, and again we're going to think about it being a constant. So now it's just a math problem, and how can we solve this? So the technique that we are going to use here, so technique here is called separation of variables. And the idea is solving a partial differential equation like this is really hard. It's going to have x and t, and it's going to have all these parameters, f of x, or which we said is c0 here for the simplest case, L and D. It has all these variables in it. We want this equation that gives us that crazy behavior that we saw over there. And so we can't just guess what that function is going to look like, but we're going to say, hey, maybe it's possible that we can find some function for c. C is a function of x and t. Maybe we can find one function that just has x in it and another function that just has t in it, our other independent variable. And maybe if we multiply those together, that we can then we can come up with something that will satisfy all four of these equations at the same time. So we will assume there is a function such that, or I guess there's a function such that, so c of xt is equal to some function x, x of x, so this is a capital X as a function of little x, and then big T of little t. Okay, so it's a product of these two functions. Okay, it is a product of a function of x only, which we're calling big X, times a function of t only, which we're calling big T. Okay, so c of xt is x of x times t of t. So we're just going to guess maybe this works, and then let's just see where this takes us. All right, so x, so again, this might be, as an example, maybe this comes out to be x squared, and then maybe this comes out to be e to the minus t. Maybe x squared times e to the minus t satisfies all those, and you can take its derivatives and put it in and see it's not going to work. Okay, but maybe there is one, so let's see if we can figure out where this takes us then. So the first thing that we need to do here is we need to replace c with these other two functions here. Okay, so we need to take the derivative of the product of these two with respect to t, and then its second derivative with respect to x squared. Okay, so dc by dt would be the derivative of this with respect to time, and so this is a function of time, but this one isn't, so it's a constant, and so that just becomes x of x times dt by dt, and then d squared c by dx squared, likewise, this is a constant, and I need to take the second derivative of that, so it's just going to be big T times d squared big X d little x squared. Okay, and again, these have this function, they're functions of that. So if we then go back and make this substitution, then we get, so I've written d big T by dt. I could write that as like prime. Okay, so instead of writing it this way, so we'll just say that big dt is equal to t prime, and likewise d squared big X by dx squared is equal to big X double prime. Okay, for shorthand. And so then if we put that back in, we can say x times big T prime is equal to d times big X double prime times t. Okay, I think I have that right. Yeah, and so this is where we get into this idea of separation of variables here. So for this to be true, I can rewrite it, I can group terms, and we can say that x over x double prime has to be equal to, or actually I would want to write it upside down. So x double prime divided by x. So move this over here and then move that over there. It needs to be equal to t prime over, and we'll put the diffusion coefficient along with t together. All right, so this is just moving this x over here and the dt over there. And if those two things are equal to each other, since they're both, so this is a function of t only, and this is a function of x only, that means that they need to be equal to a constant. They can't be equal to some variable function. There's no way it would work out unless it's a constant. And it turns out that that constant needs to be negative. And so to ensure it's negative, we will write it as lambda squared. So anything squared becomes positive, and you multiply it by negative, it's going to be negative. And it turns out that there's going to be a square root of this, so it's handy to have that squared there anyway. So this is some, so the ratios must be a constant and negative for this to be possible. Okay, because again, if it's some function of x, its derivative is a function of x, you make this ratio, and likewise with t, those things aren't going to be equal unless they're equal to like a constant like 5 or 10 or something. And the reason it needs to be negative is for this to be stable, we need it to dampen out over time. So this term is going to blow up if it's not negative. All right, so for it to be stable. So that's why it's a constant. And so if that's true, now we can take these separately. So we can take the t part with the lambda squared, and then we can take the x part with the lambda squared and see where that goes. Okay, so next up, let's do t. So therefore, we can solve for x and t separately to figure out what the relationship needs to be with lambda, and then put it back together. And then put together. Okay. And so for taking t first, we have t prime is equal to negative lambda squared times t, dt, I guess. So looking at this one first, and then the other one is x double prime over x is equal to that. So this is the t one, and we've done this, presumably you've done this kind of equation before, so big dt by, so again, big T is some function of time. All right, so the solution to that one, again, we've done it so many times, it just ends up being T as a function of little t is equal to some constant here, which we will call A times e to the minus lambda squared t. Okay, so again, this is like a constant of integration. If we write big dt there and put it together, integrate, combined terms, this is what we get. Seen it many times before. Now let's look at x. So here we have x double prime is equal to minus lambda squared times x. And this one is harder, so we need a function that if you take its derivative twice, we get the opposite of that. And so oftentimes if these are together, you end up with an exponential function here, like e to the lambda t. But that's not going to work in this case because we need it to change sign if we take its derivative twice. And so the equation that's going to work for that is going to be sine and cosine. So the derivative of sine d by dx of sine of x is equal to cosine of x, and d by dx of cosine of x is equal to minus sine of x. And so we take the derivative of sine and we get cosine, the derivative of that we get minus sine, and boom, we've got it, almost got it here. We just have a lambda. If we throw a lambda inside here, then the first derivative becomes a lambda times cosine lambda x, and the second derivative becomes a minus lambda squared. And so we've got it. And this will work whether we start with sine or cosine. So if you do cosine first, then we get minus sine, and then we get minus cosine. Okay, so there need to be two solutions because it's a second derivative. So our solution then is going to be x as a function of x is equal to some other constant. So we already used A, capital A, and C is for concentration. So we'll do B times sine of lambda x plus, we'll skip the C and go to D times cosine of lambda x. I believe I have, yes. Okay, and again, these are integration constants. So sine and cosine will work, but it turns out if I multiply them by a constant, it will still work. And then if I add them together, so any linear combination will work. That is, if I multiply, these two functions are quote unquote linearly independent. This is an important term that's used for the math here. So there's no way I can take sine and multiply it by some number and get cosine. Yeah, so they're two linearly independent functions, and but if I take sine and I multiply it by a 2, like if I started with 2 sine lambda x, the first derivative would be 2 lambda cosine lambda x, and then the next one would be minus 2 lambda squared sine lambda x, and it would work again. So there's an infinite number of solutions, but they all should have the form of some constant times sine lambda x plus some other constant times cosine lambda x. Okay, and so if that's true, then that tells us that our function here, hey, we're making some progress. C of xt needs to be x of x times big T of t, which is b sine lambda x plus d cosine lambda x times e to the minus lambda squared t, right? Times an a there. This should have been an a. And it turns out, so there's an a here and there's a b here. These are unknown constants that we need to then figure out. So if I take the a and b, put it together, I've still just got some other unknown constant, and likewise with a and d. So while it looks like there are 3 of them, really there's only 2. So I'm just going to write it as my solution should be, make sure I write it consistent with my notes so I don't make a mistake. A sine lambda x plus b cosine lambda x times e to the minus lambda squared t. Okay, so this is our solution, and then our challenge becomes, can we figure out values for a, b, and then we've also got lambda, so we got 3 unknowns here, and we need to find those, and we can do that one by using our initial and boundary conditions. So I will pick up here in the next video, and we'll talk about how you can find the constants.